is the Year 13 summary notes on simple harmonic motion for level 3 NCEA. So, what is simple harmonic motion? So, it is a periodic or oscillatory motion which obeys two rules, and the two rules are that displacement is proportional to acceleration, or you could even say displacement is proportional to restoring force. And the second thing is they both act in the opposite direction. And these two graphs here show that it is simple harmonic motion because the straight line through the origin tells you in this case the acceleration is proportional to displacement, or in this case restoring force is proportional to displacement. And because it has a negative gradient, you say that it acts in the opposite direction. There are some terms used in simple harmonic motion which you need to be familiar with. The term displacement is the distance from equilibrium. Equilibrium is the center position. So in this one, it's displacement to the right, and this is displacement to the left. Okay, amplitude is maximum displacement. Period is the time taken for one complete oscillation. So if you have a pendulum, one complete oscillation is from one end to the back, or it's from the middle all the way to the other end and back. And frequency is the number of oscillations in 1 second. Equilibrium is the rest position, and at the rest position, displacement 0, acceleration 0, because these two are proportional to each other, but velocity is a maximum. That means it goes fastest when it's going through equilibrium. At the end position, so these are the end positions, maximum displacement, it stops before it turns back, and if displacement is maximum, acceleration is also maximum, but you need to remember that both the acceleration and the restoring force are always directed towards equilibrium, so it's opposite displacement. This equation here defines simple harmonic motion, saying that acceleration is proportional to displacement and acts in the opposite direction, and the constant of proportionality is angular frequency. Okay, omega squared, where omega is 2 pi f, or 2 pi over t. Reference circle is a circle that's associated with simple harmonic motion. The reference particle travels anti-clockwise at constant speed, and this constant speed is a omega, and it travels with constant acceleration, which is omega squared a, and it travels with a constant radius, which is the amplitude of SHM. Now, why do we need the reference particle? It makes it easy to solve problems of the simple harmonic motion particle because the velocity, displacement, and acceleration are always changing for the SHM particle. So how does that help? So the maximum values for the SHM particle for displacement, velocity, acceleration are the constant values of the reference particle. So maximum displacement is your amplitude, which is the radius of your reference circle. Maximum velocity is the constant velocity of the reference particle, and this happens when it's going through equilibrium. And maximum acceleration is the same as the acceleration of the reference particle, and that happens at the end positions. Okay, there are two lots of equations for simple harmonic motion for finding out what is for timing. One is for timing starting at equilibrium, and the other one starting at the end position. So here are your equations, and these graphs kind of match the equations. These are given to you, but you just need to make sure which one's equilibrium and which one's the end position. I've just done a little example on how you actually use a reference circle to solve problems. There's more than one way of doing it. I've done this where I'm leaving my calculator in the degree mode because I'm going to use omega t in degrees, so I'm using that as theta because theta is equal to omega t. However, if you're going to be using omega t, because omega is in radians per second, your calculator has to be in radians. Okay, so this is just an example. If the amplitude is 0.1 meters, period is 4 seconds, so this is my big hint. If you're given the period and frequency, the rest of it becomes dead easy. What we're trying to find out, what's displacement when timing starts at the end, at the equilibrium position, and what's the displacement when time is 1.8 seconds. So this is how I go about it. I'm using this information so that in 4 seconds is the period. So the period means it going from all the way around the whole circle, and that's 360 degrees. So it does 360 degrees in 4 seconds. So in 1.8 seconds, how much does it do? And I just used the proportion method and I got 162 degrees. So once I found my theta, then I just used this equation, but instead of omega t, I've just used theta. So y equals a sine theta. So that's my amplitude, 0.10, sine 162 degrees. Again, calculator in the degree mode because this is in degrees. And I got this. Now, how did I know where to draw this diagram? So this is how I figure out. Timing is starting at equilibrium and period is 4 seconds. That means it's going to take 4 seconds to go from there all the way back and there. So it's going to take 1 second to go from here to the top, another second to come down. So that's 2 seconds, but we got 1.8. So that means it's somewhere here between the end position and equilibrium, but it's actually going down. So that's my phasor. My phasor is actually turned through this whole angle. So that's what I've got, and that's my 162 degrees. Okay, moving on. You need to know these equations are given to you. These are two examples of simple harmonic motion. One is a spring, one is a pendulum. You just need to know which one's which. So this one tells us that the period of the pendulum depends on the square root of the length of the pendulum and of course the value of g. And for the spring, the period of a spring, that means the time it takes to go up and down once, depends on the mass at the end of the spring and how stiff is the spring. So K stands for spring constant. The stiffer the spring, the shorter the time it'll take, so it'll go back and forth really fast. Okay, so your frequency will be higher. Just remember T is 1 over F. Okay, free oscillations. So anything that's free to oscillate, if you disturb it, displace it, and you leave it to oscillate, it will do so with its own natural frequency. How do you know what's a natural frequency? Using one of these equations. Forced oscillation, if something's already oscillating and there's an external force that's also applied to it, then the whatever is oscillating will vibrate with the frequency of the driver. That's your external force, but the amplitude will be small. Okay, what's resonance? When the frequency of the driver matches the natural frequency of the observer, then there will be few energy losses and the object will vibrate with very large amplitudes, and this is called resonance. I'm just going to write, but the amplitude will be small for forced oscillations. Okay, that's something that's important. Okay, and damping. So if there were no energy losses, you had a pendulum that was oscillating in a vacuum, then the amplitude of it would go on forever. The amplitude will stay the same, and these are called undamped oscillations. However, in reality, if you set something oscillating, after a while it will come to stop, and this is and then you will notice that initially the amplitude is quite large, and after some time the oscillations die down, the amplitudes become small. What's important is that the period is the same, even though the amplitude is different. That's the time taken for one swing has not changed. These are called damped oscillations. Okay, and this is useful in shock absorber. Some things damping is desirable, some things damping is not desirable. So you have shock absorbers where you want a lot of damping because you don't want something to keep bouncing up and down for a long time. Then energy and SHM. So the energy changes that take place for something that's oscillating is between kinetic energy when it's going the fastest and potential energy when it's at the end position. This potential energy could be gravitational potential energy if it's a pendulum, or it could be elastic potential energy if it's a spring, and these are the formulae for the different forms of energy. I hope